Hello guys, welcome to another video, and in this video I'm going to be going over problem A of the IOI 2024, which is this year. So this problem is kind of interesting, but there is a lot of things to go over. There's just so much I have to handle at the same time. Hold on, let me get this. But yeah, so I'll be going through it and I'll go over the general idea. So I need to open this. I was debugging one test case and yeah. So let me label this. This is W, and this is A, and this is B. Okay, so let me explain what the problem is. So you basically, for any given value D, they define D as the maximum difference between pairs of weights. You can put artifacts by by itself or with another artifact. So you can only put maximum of two artifacts in one boat, and they made it explicit that it's always cheaper to put two artifacts together in one boat rather than both artifacts in their own separate boats. So we want to figure out what is the minimum cost to put all the artifacts, and the value of D actually changes. So to recap, we have up to 100,000 artifacts with their own A and B values, as well as weight W. And we have some number of queries, which is also pretty big and can change. So how do you do this? Well, so first we sort by the weight. So I'll just zoom out here and I'll do sort by weight. This is because the actual positions of artifacts don't matter. All you care about is the difference in weights. So this way, when we want to consider any pair of artifacts, we can just consider the adjacent ones, because then that's the best you can do to minimize the difference. So next, we have to basically answer queries in increasing order. The key insight is, so if we, let's say I would have example value D equals 5, right? And we basically figure out, well, I'm not saying literally in code, but figuratively we figure out the continuous subarray such that their adjacent elements, the difference is at most D, so that means this will be its own subarray because difference between 10 and 2 is 8. So, and these three are in the same subarray because 10 and 2, the difference is 2, and then 12 and 5, the difference is less than 5. So that means for all the artifacts in the same array, you can take them in pairs. So this is for a fixed D. And if we increase D to like 10 to the power of 6, then we have this merging process where we merge subarrays together. So everything can be taken by pairs. without having to worry about anything. So that's the main reason why we want to answer queries in increasing order. So now let's talk about how to calculate the scores for each of these subarrays, because then the answer for the current query is just the sum of the scores. So then I'll say, I'll just use a red calc answer. So sum of best answer for each subarray. So we know if the so let me just make up some random numbers. So if we have like, let's assume we can let's assume this is one subarray. So obviously if the length is even, then we can just take it by pairs like this. So then we have sum of b, sum of the b values. But what if the length is odd? What if I have this 6 right here? What do we do? Well, when we have odd length, we know for one element, we need to take a of I instead of b of I. So then we can, so for example, if we were to take a of I for 6, then we say like plus a of 6 minus b of 6. This is because we already add up b values for everything. And the problem makes it so b of I is always less than a of I. So when we want to take a of I for something, we can just add the difference between the b and the a values. And that would just make it so that element we took a of I. So then we go back to here. So now the question is, which element do we try to take a of I on? And we'll worry about how do we deal with this merging process later on, in addition to figure out the best element to do a of I on. So turns out if we make any even index a of I, then everything just works out. So for example, if we want to take a of I for this one, then we can see everything will be fine because these can still be in pairs. This will stay the same. So that means for any even index, we fix to be a of I. We don't affect the rest of the elements. The rest of the elements can stay at b. It's just this element stays at is fixed to be a. So this kind of implies that for each subarray, we should keep track of the minimum. So say min of b of a of I minus b of I for 0 I n and I mod 2 is equal to 0. So this is one thing we keep track of. Now this is the simplest case because the best, because everything stays at BFI and just one element we increase the AFI, so we want to increase it by the minimum amount. So that's for even index. What about odd index? Well, let's say we pick this element. Okay, then what can we do? Well, it turns out, because remember, with this, we also have only one element that turns into A of I. So we want to keep it to be also one element we can take A of I on. So if we try to like let's try to figure out how can we do the fix this. So we can see that I've split the array such that each half we cannot take everything by pairs because there's these elements are left out by themselves. So what can we do? Well, notice that this array becomes a subproblem its own because now you're saying, okay, how do I take away one extra element with this? Well, if I if I also make this to be A of I, then I'm left with these subarrays, and they're by themselves, so they also have to be taken as A of I. But if I take this element to be A of I, then these can be taken as a pair. And this is only one half. I would have to do this for one other half. But what you may notice is if I do try this, if I try to fix it like this, I end up with having at least two elements being A of I. Whereas if I only consider the even indices, then only one element is to be A of I. So, but does this mean we should not consider odd indices? Not necessarily. We still consider them, but under one condition is so if we consider index I and I mod 2 is not equal to 0, then what we do is and take if I plus 1 minus if I minus 1, let's equal to D. So I'm saying if I look at this 3, right? If I can take these two as a pair, okay, their difference is smaller than D, then everything else will still be fine. So it's the two elements right beside the element I want to fix to be A of I. So this way, only one element has to be A of I, just like this one, except we have a more strict condition. So instead of considering directly adjacent, we consider elements that have a distance of 1. So this is how we kind of figure out the best optimal score for one subarray. So that means if we were to run this on the entire input, we would solve subproblems 1, 2, 3, 4, 5. Automatically, 5 subtasks solved because we only have 5 different D values and we can just go through the entire array in one go with this. Okay, so now let's go back to, of course, the full problem, which is the amount of different d values can be large. Hmm. So I'll just say this is here. So we calculate best answer for each subarray. So let's go back to this guy. Answer requires increasing order. So of course, when our d grows big enough, then some adjacent pairs that are previously not possible are not possible. So that means we kind of unite the subarrays. So how do we do the uniting? It has to be efficient. So this is where union find comes in. So say unite subarrays. So then for each subarray, we want to keep track of, I'll call this increase of some parity, where it's like a 0 p 1. So we say that for this subarray, the minimum the minimum AFI and BFI, right? So this is a parity we're talking about. And there's a reason why we want to keep track of it both for both parities of indices, even though we only use 0. If we only use even indices here, because it's for the merging process. So we keep track of this, and we also keep track of ink 2. This is the same thing. So this is for adjacent elements. So two adjacent elements right next to each other. And we have this other thing for this right here, where we consider like we consider this increase if we're looking at different two elements beside it. So I'm just gonna erase this. I'll come back to this later on. But we also want to keep track of L and R for each subarray. So this implies we can get the length. So a little bit more detail on how the merging is gonna work is well, I guess I'll just do it here. So if we're merging two subarrays, right? So this is length 3 and this is length 7. So that means when we merge this will become a subarray of length 10. So of course when we merge these we want to, because we keep track of these information of minimum increases for both parities of indices. So that means if you want to compute the minimum increase for the even indices in the resulting array, it kind of looks like this. Like the positions we consider kind of looks like this. 4, 5, 6, 7, 8, 9. So we can see the indices we consider the first subarray starts at 0, but then it starts at 1. Just simply because of the parities of the lengths of the array. Well, it only has to do with the first array because if the length of the first array is odd, let's just say you want to look at even indices when everything gets combined together. So that means in the second array, we should look at odd number indices just because of the way it gets combined in the resulting array. So that's why we need these two. This is because, so this is for account for parity. So you can see, in other words, if we want to figure out the minimum increase for odd output indices, so we start at 1 in 3, and then we start at 0 in the second subarray. So this is kind of why you do it. And of course, you can get the length by LR. So we do this, and let's go back to here. Now that we kind of go on a merge process, let's list the first sub step. So we remove old answers and add new merge one. So the idea is to, when we go over the queries in order, then we keep track of the current answer. And the current answer is the sum of this. So as you see, when we merge the subarrays, we should remove the answers. We should move their answers from the total and add in a new one. And this is how we calculate it. So yeah. So that's pretty much what we do. And is there anything else I should go over? Not really, except I'll show you a trick on how to account for this. Because turns out there's a way to do this. Like, I guess I'll just go over the implementation. I can explain it there. So after I got my data, this order just helps me with iterating over the correct order for the weight and the queries. And these two arrays, they're for the process of merging. So again, it's like when we go over increasing values of d by order, as the value of d gets larger, the more things I can merge because then the pair of some adjacent elements become legal. So I do kind of two pointer approach. So I actually do 3 pointers. I'll get with a third pointer later. So do 2 pointer approach. One for going over the queries, and second for going over the differences of the pair to efficiently merge it. And then this merge process, I basically just do, I com I compute these three information for the new subarray and I calculate the answer. And also keep track of the sum for each subarray. And then here the calculation for the score. I guess the answer for its subarray is like I mentioned. So we start off with all the B values, and then depending on whether we're odd, if we're odd, we have this extra number we add to it. Again, this is because when we're odd, we have one element that we have to make A of I. So this is for the even indices. This is for odd index. See. So just calculate this. As you can see, when I merge, I remove the two answers from the two subarrays I'm merging and add back the new one. So that becomes my updated current answer. And then this third pointer here is basically this one, but I have a separate merging procedure for it. So that's all it really is. So the general idea is I go through each query, iterate over the two other pointers if the differences are small enough. So I keep merging all the subarrays when possible. And the answer to the current query is just the current best answer. So yeah, I know it's kind of hard to explain because there's lots going on, but that's essentially how I solved it. So the total time complexity is just something log n because of sorting, but otherwise everything else is linear time. And then you just have some code for setting up the union find to help with the merging and all the good stuff. So yeah, GG's.